Now, when it comes to the elliptical orbits, we have already gone through the mathematics of the elliptical systems. So here we can see that we have two bodies of equal mass. Mind you, we are not talking about different masses at all, because then it will become a more involved case, but the idea essentially remains the same. Here, because the two masses are the same, the two ellipses will have the same semi-major axis. The A of the ellipse will remain the same, and that becomes the one of the foci of the ellipses. For this particular ellipse, it is this foci. For this particular ellipse, it is this foci. And this point at any given time is the center of mass of the whole system, which means that any given time, if you join a line to join the, if you draw a line to join the two masses, then this point is the center of that line, simply because the two masses are exactly the same. And at any given point of time, these two masses will be diametrically opposite to each other. Of course, what happens when you have different masses, which I am not showing out here, but you can understand the ellipse will change. But they will always be diametrically opposite to each other. And this point of center of mass will always be the foci of the two ellipses. So that is how you can join the two ellipses. You can draw the two ellipses. Okay. So this is a static representation of such a system, where you have one mass heavier than the other mass, m1 is greater than m2, and this point, the blue cross, the blue plus, is the center of mass of the system, and this mass m1 moves in this particular ellipse and m2 moves in this particular ellipse. Okay, so these two foci will have a say in the respective orbital path, because when it comes to, you have to understand that when it comes to the Kepler's second law, you have to measure it from this particular quantity, okay, because this is your center of mass of the system. And of course, Kepler gave his laws where you didn't consider m2 to be similar with m1. We always consider m2 to be negligible m1, and we neglect the effect of m2. Now, when we are estimating the parameters of a binary system, these are the parameters that characterize a system. Okay, so we need to look at the period of the orbit. That is one of the first things that to measure. Whenever you are measuring any periodicity, any phenomena that has a periodicity in this universe, the first thing that to measure is the periodicity. Next, we want to measure the size of the orbit. And of course, this is essential if we are talking about the visual binary system, where you can spatially resolve both the masses. Then it is extremely important that we should understand the orientation of the plane of the orbit. It might happen that you have an ellipse with has a foci here, and the object is moving like this. Semi-major axis is along this direction and you are in that direction. That is your line of sight, and this is the direction of the semi-major axis. Now, in the universe, there is no preferred direction, and hence this direction can change, randomly. So the orientation of the ellipse will be random. So that is something that we have to take into account when you are doing observation. Then comes the inclination of the orbit. So if I have this as a plane of my orbit, it can be inclined also, right? We'll talk more about this in the subsequent slides or in the subsequent video. Then we need to know the eccentricity of the orbit. So now we have to talk about the property of the ellipse. How circular it is, how much circular it is, or how much deviating from the circle it is. Then, of course, total mass of the system, because to understand the dynamics of the whole system, we have to know the mass and the velocities of the two stars. Now, you see, when it comes to two objects which are spatially resolved and you can see them over the whole binary period, then all of these you can kind of measure directly. But as we go to the different classes of binary star system, then we will realize that in certain class, we measure certain properties directly, and the other quantities are calculated or inferred from the measured quantities. So, here, this gives you an example of the concept of inclination of the binary orbit that we're talking about. Okay? So, this is a ellipse, and this orientation will actually change in 3 dimensions. Okay? It depends on if this is the ellipse, the black ellipse is the actual orbit that you are that the objects are moving about. Mind you, here we are drawn only one ellipse, okay? So basically, to keep the diagram simple, you are following one particular mass. You are not drawn the ellipse of the other mass. Now, this is the actual orbit, and here is the observer. Okay, this plane, the blue rectangle, is the plane of observation that the observer from the Earth can see. And hence, the observer will see only a projection of this orbit. So, although this is an ellipse, it will be projected as a different kind of an ellipse. And mind you, if this is a circle, then too, this will appear like an ellipse. Simply because of the projection effect, the radius in one direction and the radius in the other direction will not be the same. And hence, most of the time, what you see when you observe the systems is that you observe an elliptical path. And then by measuring the inclination angle, you have to come to the conclusion whether the orbit is actually elliptical or is it nearly a circular. Most of the time, their orbits are not circular because circular orbit is a very, very special case of ellipse. Most of the time, it is deviating from the circle, and hence we have to obtain the parameters of the ellipse. Now, let's look at the inclination of the plane of the orbit with respect to the line of observation. So, you can see this is a rectangle which gives you a plane on which this ellipse is drawn, and you have the two foci out here. So, now understand that this dotted line which gives the dotted rectangle is the plane on which the observer is viewing the binary system. And hence, actual rectangle, if you observe it along the parallel line, okay, the plane, if you observe it along the plane that is parallel to this ellipse, this is how its actual plane is. But the observer sees this particular plane because the observer is perpendicular to this particular rectangle. So, observer is looking at this plane perpendicular to this rectangle, either from this direction or this direction. And hence, the observer will see only a component of these separation of the foci. So, if I is the angle between the actual plane and the plane of projection, of the observer, then this separation will be modified by the cos I parameter out here. So now what you see is that you will see a component of the projection. So the the semi-major axis that you measure, is actually a component of your inclination. It is proportional to the inclination I. Okay, so when I is 0, so when this solid rectangle, it coincides with the dotted rectangle, that is when I becomes 0, and the observed I is the observed A is the actual A. Okay, and then if you go through the videos in which we dealt with the mass function of the system, you will realize that your m1 plus m2, the total mass function, then becomes proportional to cos cube I. Okay, so this angle of inclination is a very, very important property that needs to be measured. And it is the most difficult component that can be measured directly, because you have no visual indicator of whether what the angle is. So this is a quantity that you normally infer after fitting the data. So you infer other physical quantities like the distance, the velocities, the masses from other observations or other physical parameters, and then you fit the physical parameters and use statistical techniques to measure which is the most probable value of I. So this is where your statistical techniques become very, very important. And if you have gone through the first video where I introduced the whole timeline of the binary observations, there we had stated that the development of the statistics played a very important role in understanding and characterizing the binary systems. So, this is how you can visualize this particular setup out here again. Okay, just trying to give a more clear visual effect of what the system is like. So, you look at it, you will look at these 2 points out here, they are the actual focal points. Okay, now this point is the focus of the observed ellipse, and this is the projected focus, okay, in the plane of the sky. So now you have to make the corrections accordingly. Okay, so this is the most difficult part of characterizing a binary star system, especially the visual binary star systems. Okay, so here you see this is the observer on Earth. This is the relative orbit. This is the apparent orbit on the plane of the sky as seen by the observer. Okay, and then we have to look at the projected focus and the focus of the observed ellipse, because the whole orientation is changing. Mind you, I have to understand this, very, very important, that when I have a rectangular plane, okay, we are assuming out here it is oriented along this direction to the observer, but it can be oriented like this also. Okay, so that changes the orientation of the ellipse, and this is the angle of inclination, right? So basically, you have to understand the whole concept of 3D rotation, the Euler's angles, and then only you will be able to get the proper positioning of the foci after transforming from what you observe.